Welcome everybody. Hello. Another in our series of talks online. Thanks everyone for joining us. My name is Daniel Bennett. I'm the AILA South Australian State President, and I'm very pleased to be hosting you all tonight and our very, very special guest. Thanks to Sally Bolton as well, our State Manager, for helping organise things. So welcome and hello. Wherever you are around the world, I believe it's very exciting to be reaching a whole lot of new people to talk about something very, very important. So our event is called Climatopias, Sensing and Computational Methods in Landscape Architecture Research, and it will be presented by a very special guest, Dr. Carlos Bartesaghi Koc from the University of Adelaide, a great new Adelaidean, and we welcome him with open arms and very much looking forward to hearing more about this really, really important topic tonight. But just firstly, a couple of things. With such a large crowd, what we'd really like to do is make sure that you are on mute, and for the purposes of Zoom not crashing on us, turn your video off. If you're having any troubles hearing me or Carlos or Sally, and we do have a chat function, so please make sure through the presentation that you drop any questions in. We'll have time for Q&A at the end. Now, most importantly, just before we start, as is customary in every AILA event, I would like to do our acknowledgement of country. And I would like to begin by paying my respects to the traditional custodians of the land which I'm chairing this event from, in this case, up here in the Adelaide Hills. We acknowledge and respect Aboriginal and Torres Strait Islander peoples of Australia as the traditional owners and custodians of our lands, waters and seas. We recognise their ability to care for country and their deep spiritual connection with country. We honour elders past and present whose knowledge and wisdom ensure the continuation of Aboriginal and Torres Strait Islander cultures. So once again, welcome, hello everybody. The Australian Institute of Landscape Architects South Australia is delighted to introduce you to the Uni of Adelaide's newest colleague. But just before we get going, just a quick intro. Obviously 2020, many say, is our most forgettable year. Perhaps it's one of our most critical. As most Australians know, we've had arguably our most devastating bushfires late last year and early this year, and then rapidly followed by this economy-destroying little virus known as COVID-19. So coupled with the climate and biodiversity loss emergency that so many organisations declared in the last few years, our way of life is being challenged like never before. So landscape architects have such a critical role to play, working in natural systems, cities, regional areas, and rural areas. Our expertise and approach and thoughtfulness is now more important than ever. Climate change is real, it's happening, as all of us know, and so more talking and action in this space is always welcome, and we're really looking forward to tonight. So just a bit about our speaker. Carlos is a lecturer in landscape architecture at the University of Adelaide, has completed a PhD in planning and urban development and master in sustainable development at the University of New South Wales in Sydney. And a great history here, Bachelor of Architecture as well from his home country of Peru. His PhD dissertation received the inaugural Dean's Award for Outstanding PhD Theses in 2019. Carlos transitioned into academia at the University of New South Wales in 2015 as a sessional lecturer before starting his postdoctoral research fellowship in 2018. Afterwards, he became a lecturer in architecture at Deakin University, and over the last 13 years, he has combined teaching and research positions, consultancy activities, and practice-based design in Australia, Peru, and Chile, excuse me. Long day. As a landscape architect and climatologist, what a great duo. His research has recently focused on the thermal performance of green infrastructure on the urban microclimate by applying a systems thinking approach. In particular, he's focusing on performance-based analysis of cities, neighbourhoods, urban precincts, streets and buildings from an ecological and holistic point of view. Fascinating. Carlos' second research focuses on climate-sensitive, generative and responsive landscape design supported by computational and sensor-driven technologies such as AI, machine learning and remote sensing. Extreme urban heat can severely affect the health and well-being of the community, as we all know, in Australia in particular and around the world. And that has an impact on the environment and economic performance of our cities. Many of these problems are likely to become, or will become, more severe in the future, partly due to significant urbanisation and densification processes, but also because these are exacerbated by the impacts of climate change and global warming. In particular, for those living in Mediterranean climate zones or semi-arid areas like Adelaide, the effects of an increasingly hotter and drier planet have become more obvious and significant. Reducing urban overheating and improving outdoor thermic comfort conditions are critical aspects that should be addressed by both researchers and practitioners. In his talk, Carlos will present the most recent research projects he's been involved with implemented methods such as GIS or geographic information systems, remote sensing with satellite and airborne-based imagery, meteorological data, point cloud modelling like LiDAR, many of us now are familiar with that, which is light detection and ranging, as well as computational tools such as Rhino and Grasshopper and climate simulation. So once again, welcome everybody. If you have any questions along the way, please use the chat function. Sally and I will monitor that, and we can also open the floor to questions at the end. This presentation will go for about 50-55 minutes. So sit back. I hope you've got a nice cold something in your hand or close by, and enjoy the presentation. Carlos, over to you and welcome.
Hi, Daniel, and hello, everyone. Thank you so much for the introduction. I think you pronounced very well my last names. And all the bio and all the preparation. I mean, all the concepts and ideas and keywords. So you paved all the road before my presentation. So I really thank you for that very eloquent introduction. And also I want to thank Sally and both of you, of course, AILA, for giving me the opportunity to present my work. And so I hope you enjoy what I have to show today. So if you have any questions, just pop up in the chat, or at the end also we can have a chat if you want, just to make it a bit more human. We can chat with each other. So now what I'm going to do is I'm going to share my screen. Just cough. So let me, I hope you're able to see this. And here we go.
Yes, we can see that.
So that's it. I think this.
Good to go.
That's a big old word. Sorry, I don't know what's going on. Wow, every time I'm doing this. How can I minimize this name? It's occupying all the space. Anyway, just give me 1 second just to go back. So I hope everything looks good now.
Yes, perfect.
Perfect. So today I will present my presentation is about Climatopias, which is a combination. I just was very playful with the words. I just wanted to combine the climatic utopia, where we are really facing in these latest years. Is just a dramatic change in urban temperatures, severe urban overheating in most of our cities. So I just want to show key projects, or 3 of my most, they say, relevant projects on sensing and computational methods. Includes not only landscape architecture, but also a combination of different scales. So it goes from architecture into the landscape and also urban planning and urban design. So I hope you enjoy it, and here we go. So before, just to start with the projects and with the science, I would like to start with the science fiction, not with the science, but the science fiction. And many of you may may recognize what is the background here in my screen. If any of you have a small clue, this is one of my favorite science fiction TV series in Netflix. I'm not promoting Netflix, but yes, it's a very good one. I recommend you to look at it. So if any of you have any clue, I would just ask you if you can pop the name in the chat, so I will see who guessed. This science fiction TV series captivated me because it uses the approach and the let's say the perspectives that I'm trying to implement also in my research every day. So yeah, for those, I think, let me check in the chat. There are some people who, yeah, got it. So it's dark. Is one of my favorite ones. And so in dark, they use this logo, and this logo represents something called the triquet. And the triquet is a combination. It's a symbol they use in different seasons of the TV series to show that there exists a connection between three different times, three different moments. So it's about space and time traveling, but it's also to relate to three different worlds. And I will try to use this sort of analogy to organize and to explain what it is behind my research. So the approach that I'm talking to you, talking about is let me see if it's moving, is the systemic thinking. The systemic thinking is in fact embedded in the screenplay and the idea behind this TV series. And I was very amazed when I read it about it, because it mentions that the creators focus on the systems thinking approach. These are German creators, and this approach has been there and has been in German landscape planning and research for a long time. So it was interesting. And the idea is like, according to them, everything is interconnected. So I'm using the same approach in my research. I'm using the systems thinking in which we have different parts. All these parts are not individual parts, are all interconnected in some way. We are interconnected in some way with each other. So, and they put this question at the very beginning of the TV series, which is, the question is not only where, but when and how. And this is something that also I apply in my research. It's not only important to know where is the problem, but also when this problem happened, what are the different patterns of the problem, and how the problems are triggered by different factors. So my focus is always in processes, in time, in a space, and a continuous, heterogeneous, and dynamic world. So the problem is that in landscape architecture and architects, for a long time, we have been using static elements and static methods to represent dynamic problems, and dynamic complex problems like climate change cannot really be understood if it only focuses purely on a static moment and a specific time. We try to we should analyze the problem as a dynamic phenomenon that is all the time evolving. So this concept of systemic thinking, it's also behind of what I'm going to show. There are three key, let's say, topics that are always, and all of them have the same value and the same weight in my research, which is climate sensitive design, spatial data science, and sensor-driven technologies. So what I'm going to present today are three of these projects that combine these three elements. And so one of those is the cooling performance of green infrastructure, which is a project developed in 2018. Another project, which is the Smart Climate Road in 2019, and the latest in 2020. At the beginning of this year, we completed is the urban heat island amelioration guidance and standards. But before proceeding, I have to acknowledge that all these projects are not only my projects. In fact, I'm just part of a team. So I should acknowledge, and I will in each of these projects, I will explain who were also the leaders, who were the team. As I said, in this systemic world, or in this systemic approach, I'm just part of a bigger picture. And so, having said that, what I try to do is just to contribute as a part of a teamwork, as a part of a team, and just showing a little bit what, as a team, we were able to achieve. So the first project is in fact my PhD project, but it was guided by Associate Professor Paul Ostman and Professor Alan Peters and Dr. Matthias Irger. Is the assessing in this project, I assessed the thermal performance of green infrastructure. Our partners who were part of this project were Parramatta City Council, CRC for Low Carbon Living, who just recently finished, and also multiple local governments councils in the area that I'm going to show that I intervene. So what is the problem of the overheating in Sydney? Well, Sydney has a very, let's say, the spatial pattern of climate and of climatic patterns is very obvious. We have eastern suburbs that are commonly much cooler than the western suburbs, and particularly Penrith, which is usually up to 10 degrees warmer during summer, that compared to the cooler eastern suburbs. So the patterns of urban overheating are not the traditional the traditional patterns that we know, and particularly Parramatta, which is in between. It has a completely different. Parramatta is here. They're completely different patterns, and because it's exactly in between this breaking point in which the sea breezes stop, and we have this other synoptic condition coming from the desert, so the hot desert and westerly winds blowing. So we have these two forces fighting with each other. So I was thinking I will concentrate on trying to understand what is the value of the green infrastructure, in this case green open spaces, trees and water, in reducing the urban overheating across Sydney. So to do that, to cover such a vast land area, we need to use technologies and methods that can allow us to retrieve a huge amount of information, and in a very accurate and precise way. And the best way to do it is using remote sensing. So in this case, I use remote sensing for spatial mapping. I use two technologies. The first technology, I don't know if it is, I think this thing is blocking here the view. Okay, so I use two technologies. One is LiDAR. The LiDAR it stands for light detection and ranging. It's basically this technology uses an active sensor. So the active sensor is in fact mounted in a UAV, in an unmanned aerial vehicle, or can be mounted in an aircraft. And what it says is let's imagine the aircraft. I hope my drawing skills are good. So this sensor emits a pulse. That's why it's an active sensor. And this pulse flies over the air and hits the different surfaces. And then there is a return. And this pulse returns back to the airplane and to the sensor. And the sensor can identify what type of surface it is based on the intensity of the return. And it's doing this million times, and then creates for each of these points, which has an X, a Y, and a Z, means a geolocation. It retrieves a particular characteristic. So you can get a point cloud. It's in fact a cloud made of multiple points. And with this, we can retrieve all the physical and morphological characteristics of the surfaces. And you can identify, depending on the intensity of this return, what type of surface it is. It's a ground surface, it's an artificial or vertical surface, it's part of a building, is vegetation. And you can use this to identify different physical features of the landscape. And this includes vegetation, this includes different type of surfaces, and you can filter out all these points and create this sort of analysis that you see right now in your screens. The other technology is a passive sensor, and this is a spectral and thermal imagery. So where we have the spectrum of the light, and it has different wavelengths, and of course these cameras detect the let's say the reflected wavelength from the surface. That's why it's a passive sensor, like the photographs we have, like the mobiles we have. It just detects the amount of light that it's going into the sensor. And based on that information, you can identify different characteristics. Difference with thermal and spectral imagery is like we have the RGB, the traditional visible wavelength of the light, which is the red, the green, and blue. But with the thermal and spectral, we have other wavelengths in which we can identify particular characteristics of the surface. Like, for example, the vegetation, where it is, if it is true vegetation or if it is a fake vegetation. This technology started in the Second World War, when they want to use a camera to identify if the greenery there you're looking, or the green you're looking is a camouflage, or if it is a real tree. And these were developed during the war. So it's just like an anecdote or anecdotic idea here. So what I developed here, it was a methodological framework that combines these two technologies to retrieve information over a very large land area. So the methodological framework includes, I think I need to move this back and forth. The methodological framework includes the thermal infrared, the LiDAR, and the multispectral. So you can see here the extent of the data sets that we collected. The LiDAR data sets are the square ones. These were collected from LPI, at that time in New South Wales Land Property Information Office. I think now the names have changed. This was a monitoring or data collection mission developed by performed by the government. So I didn't have any control on the quality of the information that was retrieved. We have also thermal imagery and spectral imagery. So you can see the extent of the thermal imagery and the spectral imagery over different areas across Sydney. Why this pattern? Because this is the pattern of the flight. So we have here the airplane. So this airplane was flying in this linear direction to try to have an idea of a cross-sectional information of the different conditions of thermal conditions across the city. So we have the CBD, we have the central areas, and the southwestern suburbs towards Bankstown. And on the other side, on the other hand, we have on the northern swath, we have Mossman and near the coastline, and then we have the green area near Lane Cove, and then towards the hillshire, towards the northwest as well. So southwest, northwest directions. And then of course we have Parramatta in summer, which give us a lot of information about the heat island there, particularly in summer. This data is very expensive to collect, so we were very limited by the data availability. So the next step was using different algorithms, particularly GIS algorithm in ArcGIS, but also different software such as LP360. LP360 is a very well-known software for that LiDAR analysis. The other is LiDAR Analyst and LiDAR Features. And currently I'm using Cloud Compare, which is another good software to filter this information. And I use particularly an algorithm in LP360 to retrieve the building footprints and retrieve also all the vegetation, the tree canopy and bushes. But on the other hand, from the spectral and multispectral imagery, I obtain the NDVI, which is the Normalized Difference Vegetation Index, which tells you what is the healthiness or the real location of the vegetation. And so we're able to classify or reclassify this information into generic surfaces. So the next step was to cross-validate these two pieces of information from LiDAR and from spectral imagery. So we have a physical retrieve and also a spectral retrieve that were filtered out, and then we got these beautiful buildings and tree canopies, and this level of detail for different areas across Sydney. So we have a very high resolution classification of different land covers. Next step was to estimate the arrangements of the trees, and I used two indicators, which is the name of this is a spatial indicators developed or FragStats. Okay, so I use this software developed by the University of Chicago to identify if these trees are clustered, are in a linear shape, or if they are dispersed in the landscape. And then using a conditional algorithm, I classify everything into green infrastructure types. So what are the green infrastructure types? The green infrastructure types is a new framework that I developed based on literature to be able to classify the land in different different typologies, combining different proportions of surfaces and different arrangements of trees. So we have here the main surfaces were impervious surfaces, non-irrigated grass, irrigated grass, shrubs, trees, and water. So each of these types are unique, have a complete unique, let's say, characteristics. So when you classify using the algorithm in GIS, each of these units or spatial units, in this case were 50 by 50 meters, should be classified in only one type. This cannot be classified in 2 or 3 types. So it took me quite a while to try to have a classification that is quite accurate. And I reached around 79 to 83% of accuracy of classification, which is pretty well for the first time you're trying to do this. So each of these typologies or types, in fact, this is a whole typology, has a unique combination of elements that help me then later to compare what it is the performance of one particular typology against the other one. So you have here, for example, IM5, which represents impervious, mostly impervious with scattered trees, and I want to compare if this is much cooler than the MX8, which is mixed grasses with scattered trees. So then here you will try to identify how the difference in the proportion of impervious surfaces can give you a completely different thermal profile for that particular type. So this is in terms of methodology. Here are some of the results. Particularly in this talk, I want to concentrate on the methods more than on the results. But then I want to show also some of the results to understand what are the outcomes of that methodological frameworks. So here we have the classification, all the classes. All the classes are here represented with a color, color pleth. So you can see the greener areas in the central area of Lenkov, and in Chaswood you can see that they are mostly impervious. Southern swath, you show Sydney CBD quite dominated by impervious surfaces, and so on, and Parramatta. So it has a is a good visual agreement with the existing land cover. I also perform a statistical analysis, and also I remember in MATLAB a classification learner in MATLAB who has different algorithms using machine learning to train the computer to understand if these classifications are correct. So I got between 80 to 90% of accuracy in my classifications, which was really good. I'm not going to talk about the algorithms because they're a bit complex at this stage, but it's really important to show what are the results over the landscape. So we have here, for example, one of those features in the matrix. This little frame we have here that I'm highlighting didn't want it to be classified. So because it didn't want it to be classified, just simply it was a rebel. So these ones were excluded from our analysis, and then we will have the rest of them participating of this statistical party in which we invited all of them to be part of it. So we have here, it was quite good classification. There were all, of course, errors. So we estimated our level of error. And after this classification, we were able to identify our hotspots and cold spots. Typically, the classification of hotspots and cold spots is done using different methods. You can use, for example, interquartile ranges. You can use also equidistance ranges. The most common is the Jenks classification optimization ranges, or natural breaks, in which is trying to find homogeneous groups of values and represent them. This is how traditionally our thermal mappings are, or the thermal maps are represented. So you can see in a lot of websites, consoles, I'm not saying that is wrong, it's just saying that they use the GIS algorithms that are already embedded in the software to classify within ranges. And these ranges, which is usually the natural breaks or Jenks optimization, just try to homogenize group within, statistically, within that group are quite similar. So you will see the representations in which the thermal map, you see hot areas and cool areas. But what I tried to do in this case was something a bit more complex in some way, is using local indicators for a spatial association called LISA. It's were developed by Luke Anseling at University of Chicago. So I use Geoda, which is a software, which is open source software, to estimate these cold hotspots and cold spots, not based on traditional statistical method, but using an spatial method. That means that we consider, let's imagine this is a grid, 8 neighbors around your point. So we consider similarity by value and also similarity by distance. As we know in the rules of geography, everything is related, or there is more, everything is related to everything in the space. It's the neighbors, or the closer you are, the more influential you are. So what we're trying to identify with this formula is basically the spatial autocorrelation. It means that the values next to you, next to this grid, particular grid, in this case is a GIT, is a infrastructure, this one is also in close proximity. And using this robust statistical method, we were able to identify the hotspots and the cold spots. And interestingly, the hotspots, as we assume they are always linked to, for example, impervious surfaces, are not always there. What happened? You have, for example, CVD of Parramatta that during the morning, it's really hot. But during the evening, it's relatively cool. You don't have a hotspot there. And what that happened because the presence of shading, for example. Or you have areas like this one here, that it was, this is a very dense cluster of trees. In the morning were really cool. In the evening, there was a lake here as well. I don't remember the name of the lake at this point, but there was a lake. This lake was considerably warmer and make warmer also the areas around it. But what happened is when you have a cluster of trees, all the heat in the morning is trapped during in between these different layers of the trees remain trapped during the night. So when you have a very dense cluster, this heat cannot be dissipated throughout the atmosphere. And because of that, this statistical method allows us to identify changes over time during the day, during the night, and compare also between summer and winter. So as you can see, are areas that were supposed to be much cooler at night, like were full of greenery, they end up being really warmer at night. So it was a very interesting way of exploring the different thermal conditions of vegetation. We also calculated the cooling capacity using just normal statistical methods like ANOVA, which is the analysis of variance. We also estimated this, the departure from the case or the base case. So in this case, our base case is a typological, totally or completely impervious, which is this one is the IM1. This is a typology that represents a completely lack of greenery and water. And then we compare the distance or the departure from this average value. So we identify during the day the cooling effect of different typologies, and we found that, okay, the water is really cool. But what happened with the water at night is not as cool because of the capacity of the heat capacity and the thermal capacity of the water, which absorbs heat very slowly, but then release heat very slowly as well. So then we found that, for example, again, in previous very dense trees, which is this group here, are very cool during the morning up to 8 degrees in terms of surface temperature. All this analysis is surface temperature, and it's much cooler at night. We also identified that a lot of anomalies in this analysis were represented or caused by the differences in albedo. and reflectance of the surface. So it's basically the properties of the surfaces. So the albedo represents the amount of, say, short wave radiation that and that may be absorbed. So low albedo materials end up having a lot of absorbance of heat, and high albedo materials tends to reflect most of the radiation, so they absorb less heat. As you can see here, within the same group, which is the or within the same type, we have areas that have asphalt, and they were considerably hotter. That's why they are the outliers in these box plots. And then in the same category, you have very cool areas in which you have reflected surfaces from the roofs. And so it's worth to further analysis on this particular aspect, because then it's not about only classifying the land, but it's also in understanding the different properties of the surfaces, and remote sensing can help us to do that. At the end, this is different all the sort of analysis that conducted in terms of the effects of the tree arrangements. And of course, the tree arrangements is not significant unless you accompany, for example, cluster trees with impervious surfaces. So if you cluster trees and then you surround those trees with pavement, what we have is that the contribution, the thermal contribution of the pavements will outweigh considerably the contribution of the trees. Then you are not going to have a significant surface temperature decrease. But this is all the information, all the result that I'm presenting is only surface temperature. I will talk about air temperature and thermal comfort in another projects. So at the end, this beautiful, or beautiful for me at least, green infrastructure typology helped me to identify thermal performance of each of these types and compare and try to identify which is warmer and which is cooler, and then you can use one interchangeably with other if that is the case. Now what I'm going to present is the second project, just to move forward, is the Smart Climate Road, is a climate responsive design for Phillip Street. And this project was led by Professor Matt Santamoris and the team of Professor Matt Santamoris, who is a renowned climatologist and academic in the world. Is one of the toppest in the field. So I feel really happy to be invited by Professor Santamoris to participate of this type of research. And he has, I name here all the team who participated, and I acknowledge them, all of them, because this is a work that is not possible to be done by only one person, for sure. So here, our key, let's say, client was the city of Parramatta. So Parramatta is located 22 kilometers from the coastline, or 19 kilometers from the Sydney CBD. Is the second CBD, or central business district of Sydney, of the Sydney metropolitan area. So it's quite important in terms of economy and jobs, and also in terms of the urban form. It has very dramatic urban developments happening very recently. But not only that, is because it's far from the coastline, it doesn't have the significant effect of the sea breezes, the cool sea breezes that are, as I said before, fighting against the warm, hot and warm westerly winds coming from the hot desert. So we have here two synoptic conditions that are really fighting with each other, and they found that the battlefield is exactly city of Parramatta. So city of Parramatta, as you can see here, well, this is the central area. We focus on Phillip Street. Phillip Street is located here. This is the beginning of Phillip Street and till the end of Phillip Street, because there was a plan from the local government to have a serious redevelopment of the whole street. And they were thinking, why not to create a smart climate road and then develop these using science-based design. So it's science-based, let's say, city redevelopment. So they invited Professor Santamoris and the whole team I am part with let's do something that it is a monitoring, let's do an analysis of different scenarios, and let's see what are the best design solutions to create really a smart climate road that it considers climate, or is a climate responsive road. So as you can see here, over the last 10, 15 years, not only the street, but the whole CBD has is facing a considerably growth in terms of density, population density, but also building density, and also a significant increase in heights of the buildings. So they were really concerned about giving or authorizing the developing or giving development approvals to buildings that may cause a negative impact on the area, and they may cause significant urban overheating over the next 5 to 10 years, and then they will have to remediate that in future. So we were invited. So this is how it looks, the three-dimensional model of the sites before the project. Before starting the project, then they recommend us to review what are the different impacts, what will happen when you see these new skyscrapers, seeing the new developments around the CBD. But they also want us to model how is the different temperatures of the climate conditions that may be in a particular scenario, which is a highly dense scenario, which is not so bad as we people think, but it has pros and cons and advantage and disadvantage. So these are generally the conditions of the site. So what methods we decided to use is really important. In this project, it was quite important to have very robust methodological framework. So we provide real evidence-based solutions for the site. So the first technology is the thermal photogrammetry. I'm gonna explore each of these in more detail in a few minutes. The second was the on-ground monitoring. So we have aerial monitoring and we have ground monitoring. So we have a complete set of analysis for the whole area. And with all this information, we just move into the algorithm-aided design phase, which is designing solutions that can consider all the climatological aspects that we monitor during the previous phases. And with that information, we move into the computer fluid dynamic simulation or environmental simulations using ENVI-met. So ENVI-met is a well-known and well-established CFD software that can help you to simulate or model different climate environmental conditions and parameters, including temperature, surface temperature, air temperature, mean radiant temperature, which is the like feeling, to put it in simple words. So the methodological framework started at the very beginning with this aerial monitoring. The idea is just to have using this UAV, which is an unmanned aerial vehicle or drone, is an hex. I think this is an hexadrone. It was a DJI hexadrone that has a thermal camera and a spectral camera. It doesn't have LiDAR. So because LiDAR is quite heavy for this model, the LiDAR, and it's very expensive also. So this is a drone that owns the UNSW. This project was developed at UNSW, I should say that. So what you can see here is a thermal camera that is also capturing video, a thermal video in real time. And so you can also identify the temperatures of different surfaces. Put attention here, for example, particularly the temperatures of some cars. So it's quite important when you look at the road. It's not only to look at the temperature of the asphalt. If the road is quite congested and beside the traffic, which contributes to anthropogenic heat, you will have surfaces of the cars really hot, contributing to a higher temperature of the canyon, of the street canyon. So this technology helps us to retrieve all this information. But the most interesting one is the photogrammetry approach behind. So with all this information, the photogrammetry basically is the science of taking photographs from different angles. So then in a photogrammetric software, we have a lot of these softwares nowadays available. Matterport, for example. There are other softwares like Autodesk Recap. You have Map4Drone, and so many other. Pix4D is another very well-known software that when you collect photographs from different angles, what the software is going to do is going to triangulate this information, and then it's going to create a 3D mesh. So what you see here is a 3D mesh. Instead of having visible light, you have the thermal information capture. So you see where are the hotter roofs. Oh, it moves. Sorry. And then we have the cooler pavements or the cold pavements. And you see the asphalt is considerably hotter, up to 60 or 65 degrees. Some roofs are much hotter than other ones because they have reflective characteristics, and other ones are much warmer. And also the tree canopy. Also put attention to the reflectivity of the facades, because all of this is glazing. So even though the facade is cool, most of the heat of the facade is reflected into the canyon because of the reflectivity of the glass. And because of that, a lot of that heat is trapped into the canyon. So with this information, we have a three-dimensional idea, and a three-dimensional mesh and model can help us to understand where are the different overheating patterns along the street. Second step was, is a monitoring that happens simultaneously. So at the same time we deployed the drone. It was in a hot summer, typical summer day. We deploy also on-ground monitoring, and this on-ground monitoring use both fixed and mobile methods. This is an energy bus. The energy bus was parked in the central area of the street, and it has this mast that can vary in heights, and it measures air temperature, relative humidity, and wind speed. And at the same time, we have another station that you cannot see here. Here's a fixed station. It's a MEC Pro station that measure also humidity, relative humidity, and air temperature. So the flexibility that gives the energy bus is that you can place it anywhere in the street where you want, but we decided just to use it as a fixed method. So it's fixed to a point, but we can use it that point as a reference. We have the on-ground monitoring. So this was a monitoring campaign. We were several people involved. I was not the person who organized the campaign, but they were as part of a team. We just all collaborate in different ways. So I was just going around with this trolley. I remember that day was really hot and was really unpleasant and very windy. It's a hot wind. And so we have here, again, a small meteorological station. We measure the wind speed. We measured, this is a air temperature sensor that was covered by it's for solar protection, because we don't want direct solar radiation to hit the sensor. And we also use thermal cameras to retrieve the different temperatures of the surfaces and pavements. As you can see, the age asphalt was nearly 57 degrees. Also was quite dramatic to see that a lot of these pavement along the street was considerably hot, nearly 50 degrees. So we deploy all these sensors. This is a monitoring campaign that was well developed. And we have the energy bus and the fixed station in the middle. We have also the different trolleys, this moving around with the sensors. So we monitor all the temperatures around the streets and also along the street. And we also mounted a UAV on top of the car taking photographs. And also on a second day, we have all the UAV flying over this portion of the street to retrieve a three-dimensional photogrammetric mesh. With all that information, we're able to understand what are the significant patterns, and what you can see is we use this reference, which is in the central area, the energy bus, as a reference, and then we calculated the difference with the different stations and measure points. And we found that particularly between Marsden Street and Church Street, we have a very high temperatures, and we have much cooler temperatures as you get closer to the Parramatta River. And this happened because sometimes the breezes from the ocean can travel along the harbor and penetrate farther into the land up to through the Parramatta River up to this area. So you see here exactly this gradient between the warmest CBD, where hot westerly winds, and the cool easterly winds penetrating farther from the harbor. This information we develop, or we model different scenarios. We have multiple scenarios. There was one plan that proposed the city council. Later in the results I will show you that was a plan that performed pretty bad. I didn't suggest that one, but we suggested an improved version combining reflective pavements and greenery, which perform much better. So this give us the information that was really, really good to understand if the design decisions can have a really positive or negative impact on the climate conditions of the whole street. And then we model also cool pavements, urban greenery, shading, water sprays or misting fans, cool roofs, combined version of all of these from M1 to M5. And then we also combine the greenery and shading, which is pretty similar to this option. But in fact, we added a couple of extra trees. And this was our preferred option, and this was the council preferred option. And we also simulated a new technology called radiative or daytime radiative cooling. So I will explain about radiative cooling later. But we model of these options in ENVI-met, but before proceeding to the modeling part, we conducted another analysis to understand different local conditions using computational design tools. In this case, I use Rhino and Grasshopper. We calculated the number. This is the number of sunlight hours that the surfaces receive. So you have a better idea here of where are the overshadow areas and also the overexposed areas during different climatic conditions. And for that, we use Grasshopper, which is an algorithm-based software, which is part of Rhino 3D, which you can, it's a parametric software because you can change the conditions of the parameters. You can change the parameters and automatically get a result display in Rhino. So we also explore different parametric options. So we have an exploration process, included kinetic options and also parametric options. And these kinetic options are like those ones you can see here, poetic kinetics. I just came across these videos online, and we were thinking and suggesting why not to also have a very creative and playful shading device that can vary and can play with the wind, because the wind is quite strong in the area. So we have a significant amount of wind blowing along the river and also coming from the west. So Patrick Shern is the co-founder of this company. But this is basically our installation. So we were thinking how long and how durable will be these installations. Usually these installations are just for a couple of weeks maybe or months. So we're thinking in a long-term solution may not be the best, may be useful for an intersection or for a small plaza, but we also explore different parametric solutions using different Rhino and Grasshopper algorithms. So this is what I try to model with the Rhino and Grasshopper. So it's just a surface that can adjust different heights depending on the amount of shading that we want, and also it has considers the location of the trees and the new planted trees, so we avoid them to to go over the canopy. All of this using this definition in Grasshopper. We also consider using water-sensitive urban design, so the structures were supposed to collect also water, and this water just distributed to the ground and be stored and can be used for irrigation. So we can have here a lot of greenery and green walls, and also have here different sensors installed in different parts of the shell of these structures. So there we can collect data, and then we can use Internet of Things approach, combining this data to provide different services, for example, the Wi-Fi or 3G services, but also environmental monitoring, security, and infrastructure and transport. So the idea is also they can identify, for example, if the temperature is really high in the street and the relative humidity is low, the spray water systems that we install there, they can start spraying water over the people, so it improves the thermal comfort. As you have here a fan as well, it can start blowing wind if you have a low wind speed. If you have enough high wind speed, the fans stop. If you have low wind speeds, the fans start working, so you have evaporative cooling beside the shading. And this is another technology we suggested to the council. Of course, there were all different suggestions, but this is a very innovative technology called radiative cooling. What basically is using is a crystalline nanostructure that reflects the solar radiation, the short wave incoming solar radiation, in a very, very similar angle, and you can reflect up to 97% of this back to the atmosphere in the same incident angle. So you don't see that reflected in a different direction. You see that reflected in the same angle. So it returns back to the atmosphere or to the upper atmosphere. So what happened with this technology, you can obtain sub-ambient temperatures up to 10 degrees lower. This technology is currently developed also at UNSW. Professor Santamores is leading one of these groups, and also Professor Gianluca Ranzi from University of Sydney. They are both together working with other experts worldwide, particularly the Lawrence lab in Berkeley and many other ones abroad, to develop technology that can be cost-effective and a polymer that can be applied on top of any structure, even like this structure here. So we suggested also this, and we also model it. So these are the different mitigation strategies that we distributed after all these architectonic, landscape, and urban planning exploration. We end up designing our strategies, and then we distributing across or along the whole street. And we consider areas that require more green canopy, where more shading was also recommended. Here in this location near Martin Street, there was a car park close to the police station that it was all covered by asphalt, no trees, and it was considerably hot. So when the wind blows, all this heat is distributed into the canyon, and it was a tremendous impact. So we decided also to pavement everything with a cool material. We perform the CFD simulations in ENVI-met. What you can see here is the ENVI-met domain. And from this information, we identify the different temperature reductions in the canyon. As you can see, in some cases, the most effective, specifically the combination and the radiative cooling shading, you can see a spillover effect over the surrounding areas because of the wind. So these technologies really help a lot to reduce the temperatures. And I would like here just a couple of I think it was yesterday or a couple of days ago, one of my colleagues and we're working together is Professor Rhinoceros Bartesaghi Koc. We were really concerned about one of the, I think in the Randall Mall in the CBD in Adelaide, they want to repave everything in Randall Mall because they think according to them, they have an argument that it's not climate sensitive, or because it doesn't consider the pavement the cost of the climate change. So they want to repave everything. So we were thinking it will be very interesting and very useful if either a consultant firm or academia, we can perform really quite a comprehensive study along the Randall Mole, so we can really provide science-based solutions, and not only based on anecdotic arguments. But it will be interesting to see if they are interested to do this. I think we'll get a lot of benefit, and the other colleagues in the school, they have already information and data that we can use to do a very similar project like the one that we did in the Parramatta. So now I'm moving into the last project. The last project is an urban heat amelioration. This was the idea was the Department of Environment, Land, Water and Planning from Melbourne. They were really interested to see what we can do in a similar way than the previous case, but model different options for developments and for lot scale, for a parcel scale. So Associate Professor Paul Osman and Landing were in charge of this project, and they kindly invited to co-lead it. So we developed a set of design guidelines and different standards for DELP, using, again, simulation and computational approaches. So we already know this is the new norm, or the new business as usual, what we see in the new developments, not only in Melbourne, but all over Australia. And we have a projected median hot days by 2050 that will be nearly the double. So we have now 6 days, like in 1986, we'll have 13 days of the year that will be heat wave days. So if we continue designing streets like this, in which we have a lot of lack of greenery, no trees, no green open spaces around, a lot of pavement, a lot of asphalt, and quite dark asphaltic tiles or dark colored roofs all over the place, we will have very high surface temperatures and consequently very high air and very high heat stress on people. Besides that, we will have a penalty, which is in terms of money in cooling. Building energy consumption is significantly higher in this type of development. So imagine each of these has, because that's what they offer you. Now, when you purchase one of these houses, they offer you air conditioning, so you will have more days of the year of these houses using air conditioning. Because of that, DELP wanted to develop, what we need to do is identify case studies. We want to develop guidelines for developers so they can design better cities and better neighborhoods. We identify different case study and we model these three in 3D using ArchiCAD. And then we exported that into Grasshopper and Rhino to model voxels, volumetric pixels, to put it in simple words. These were exported from Grasshopper into ENVI-met, where we model again CFD simulations or climatic simulations, and with the evidence, we develop a dynamic matrix tool and design guidelines for DELP. So these are the different locations across the Melbourne metropolitan area and Geelong. It's a huge conurbation. So we identify, guided by DELP, different type of developments. And these developments are basically, low density residential, which is a single lot, to those dual lot split, medium density residential or larger townhouses, small apartments and larger apartments, which is represented here as a high density. So, and then we have also commercial buildings and also in small, medium and large industry. So with this information, once we have identified the case study, we model all the case study in ArchiCAD in a three-dimensional model, but you can see this is an abstraction of it's a 3D model of the real case. And then we identify different scenarios using the literature. There are already guidelines available there, and a lot of literature that says which type of combinations are more efficient or effective in this type of development. So guided by this literature, we identify different scenarios for the different developments. So you see here, for example, the scenario one was just cool materials in roofs and pavements. We also added green roofs. We also model a small canopy cover and large canopy cover, a combination of materials and pave and greenery, and also green roofs combined with vertical greenery and small trees. And with this information, this is another example of a commercial center that we also model. And with this information, once we model, for example, shading, evaporative cooling, and trees, we export it into a Rhino. And so we have a Rhino model here, and then we use Dragonfly, which has a set of tools to export from a Rhino directly to ENVI-met. So you can visualize all the solutions also in 3D, all the simulations. And then we exported those ENVI-met simulations into a table. So we have an idea of which scenarios are the best performing scenario or the best combination, like for example, for the high density residential, the cooling materials and the large trees provided a quite significant temperature reduction of up to 1.5 degrees and thermal improvement up to 2.3 degrees. Surface temperatures also reduced considerably because of shading and evapotranspiration. But for example, we identified that green roofs were significant, provided a significant cooling for the building, but not for the surrounding area, because it's most likely that the air or the wind will provide these, all these cooling effects will be spread several meters above the ground, and so it doesn't have any effect on pedestrian level. And finally, with all that information, we develop a matrix, which is a dynamic matrix. What you see here is just the prototype, or let's say this is the initial draft of the tool. Now they have a much more modern one, and they are developing one using a web developer. So it's embedded on a website. So it will be ready soon. And here in this matrix, you can select the different mitigation strategies and display the simulation results, so you can understand where is the spread of these thermal conditions, of the temperature reductions, and you can select also which is the worst performing one, and also visualize it, like in this case where the cool roofs or green roofs. So then you can select back or go back to the menu, select the light industry, for example, and also choose different other technologies. Light industry, for example, we found that the tree canopy, and especially large trees and cool pavement and cool roofs, can significantly reduce urban overheating over large area. So with this information, then we have enough proof or scientific evidence to provide guidelines to the different governments and also the different developers. And at the end, we embedded this tool for this is a report that they can use for reporting the results. We designed different guidelines with this information at lot scale, and also we identify which combination of strategies were more effective. So I think with that, I would like to conclude the presentation of today. As I said, this is the same. I'm borrowing these quotes from the TV series. The beginning is the end, but also the end is the beginning. So this is not the end of this talk, but in fact, it can be the beginning of a large discussion, because we have the opportunity to combine quite innovative methods and technologies, not only landscape research, but also in landscape architecture teaching. And this is what I'm trying to do at University of Adelaide, combining reality capture and sensing, algorithm-aided design, and advanced simulation in all the courses we are delivering at AILA. So, well, many thanks for your attention. So there, anything you need, there's my contact details, so you can email me. And that's it. Thank you so much for your time. I think I went quite over time, so sorry.
That's all right, Carlos. Thank you so much. Just leave those details up there so people can download them. But of course, we will make those details available as well.
Okay.
So thank you so much. That was very, very informative and very deep and meaningful in terms of relationship to landscape architecture. Now, I've been following the chat. I think we have one question actually, and this is from Rahim, who's actually in Singapore, I believe. And his question to you is, was ENVI-met used to translate the LiDAR image into a thermal map for the first research project?
Well, in the first project was my project, I think my PhD project. We didn't use ENVI-met at all. That was completely based on empirical data. So it's information that we monitor using the LiDAR and the thermal images from the aircraft. So there was no simulation. So that's real, true, pure information retrieved from the surfaces. In the second project, we used ENVI-met to model the different scenarios. And in the third project, what we did is we used Grasshopper to really translate the 3D models into the ENVI-met interface and export it, but it creates and integrates all the different softwares together. So we don't need to model again inside ENVI-met. But I hope that answers your question. But in terms of the LiDAR, we only purely use in all the projects, in particularly the first one, for retrieving the three-dimensional and morphological characteristics. So we have the heights of the buildings, the building footprints, the height of the trees, and the extent of the tree canopy in different streets and neighborhoods. That's the LiDAR was used also to validate or cross-validate the classifications using spectral imagery. But happy to answer more questions.
Thank you. I noticed there's a little bit of chat. There's a lot of jealous landscape architects and others of your graphics that you've shown in the presentation. So a lot of commentary on that. We do have another question. Thanks, Matthew Neal. He asks, working in Rhino requires modelling at 0, 0, 0. Do you have advice for workflow between other disciplines who model in geographic locations of northings and eastings? It's a good question, actually.
Yeah, that's a good question. So we found that not in this particular, let's say, how to put it in simple words, and these particular models, what we did is it's when we model everything in Rhino and we export it in ENVI-met is when we set up all the climatic conditions and the information in terms of geographic location, northing and eastings, etc. So we avoid having that problem. But in another courses that I've been teaching, I'm trying to teach the students also to use these tools. We found that, for example, when you import GIS data into Rhino, and then you will have some problems with the 0, 0, 0. So you have to translate or move that into geographic locations. And the best workflow is to, for example, you can use Urbano or Elk or other those plugins and import it, and then later try to correct that inside the Rhino. And if you want to run, for example, like we run it with Ladybug inside Grasshopper, different climatic conditions, what you do is you grab the information from the EPW information, which is a file with a lot of the typical meteorological data for a year of the closest meteorological station, and then you model the Ladybug parameters or radiation analysis or all the analysis using that EPW, irrespective of the geolocation. But the other data, it's very complicated in Rhino, so a lot of the analysis was done, for example, using the GIS or a spatial data. So I hope this helps. Rhino has some problems with GIS, so that's why I use a combination of tools, because GIS can sort it out a lot of issues in terms of geographic location that the Rhino has as a limitation. But the other option is just to move everything, or use EPW, for example, if you want to model something ladybug from the closest meteorological station, so you don't lose that geographic connection in some way.
Thank you.
I do have a question for you. Thank you for that. That's a great answer to a great question. I do have a question on perhaps the more aesthetic side of things with some of the work you're doing in Parramatta, and having worked in local government, I understand often how challenging that can be. So well done on that climate smart street.
Thank you.
I think there's a lot of people writing a lot of things down, which is very useful. In terms of the structures that you showed us and the performance that they can offer, one of the biggest challenges or patterns I've seen in cities across, well, the world really, is that we design these things to last a long time, but political will often gets in the way, and people go, oh, that doesn't look nice, we'll pull that down. And we've seen that here in Adelaide many times on some of our streets where we have things that get out of design, and so we pull them down despite the function that they have. This starts to maybe change that conversation with performance from a climatic perspective. Yes?
Yeah, I think that, well, first, most of these most interesting projects, let's say, where we really engaged actively with local governments, because they were, particularly the Parramatta ones, they were extremely interested in what was our evidence, what we have to say. So it's really important to have this sort of communication with the local governments first. But in this case, it was the initiative. They approached to Professor Santamoris, and it was Professor Santamoris who really developed this sort of communication, and we as a team try to convince them on the best solutions. We're really pleased to see political and government approaching politics, I mean, from a political point of view, to approach to us, and because a lot of the answers we gave them were very sensitive, and because a lot of the solutions we provided or we recommended were not the most cost-effective, because there are a lot of challenging conditions to implement many of these, like in terms of technology, cost, maintenance. So we try to really give guidance to the governments on what to do. And I would like to see more of this in Adelaide, particularly, because we also are seeing hotter days there, heat waves. And so I'm very, very keen on collaborating. We have a very strong group at University of Adelaide. Currently, we are working, and we are very eager to help anyone in any local government to answer those questions. And we try to be quite impartial, and it's purely scientific proof. Then later we can enter into the negotiations of which is possible or not to do from an economic point of view, from a political point of view. We just try to keep our science unaffected and unbiased, right?
We just had Greg Ingleton is from, thank you. We've had Greg Ingleton, who's from SA Water here in Adelaide. Really interesting comment, thanks Greg, about some air temperature sensors that they've put around the city. And I think the last comment there is really interesting, that he says, we also find that surface temperature of roads is the same as unirrigated ground over summer. And that's just extraordinary, isn't it?
Well, let me digest very well the question. Look, climate conditions are very tricky. You know, climatic research and meteorological conditions are very tricky. So when we analyze a lot of data or big data over a large period of time, what we're trying is just to find a trend that can give us an indicative amount of cooling or heating, rather than precise value, which is just with for example, 2 digits of precision. It's really hard. So what we should try is just to see how is the evolution of the temperatures between one and another surface over a period of time. Otherwise, we're capturing just an average. It's very, or a maximum or a minimum. I found that there's a drastic difference between unirrigated and irrigated grass. In summer conditions and during heat waves, this difference is even more dramatic. We have a significant difference between, of course, roads and some irrigated grass. Unirrigated grass behaves sometimes like concrete. Yeah. Thermally behaves like concrete. So, but the problem is that we have this challenge of how we provide more irrigation when we have a significant or severe drought or a lack of rainfall over a period of time. So how we cannot rely only in passive irrigation. We have to rely on active irrigation, which should consider a water penalty for each square meter of grass that we want to irrigate, because that water should come from somewhere. Absolutely. So yeah. So when we're doing climate analysis, we try to be very. We should be very careful about the values that we analyze, because we have seen 1.1 degree in another studies up to 5 degrees. We should avoid also, for some reasons, we have anomalies in the data, and this might be because of a strong wind, for example. So we need to analyze holistically. We need to analyze what happens when the wind, what happens when with the shading. Sometimes we locate the we locate the weather stations in a wrong place sometimes. So we try to avoid using outliers. So we avoid the outliers always, and so we keep with those who behave properly within the group. But also, it's really important to analyze the outliers, because they tell you the other side of the story, which are the extremes. Why are those extremes happening is really important as well.
We've got probably time for one more question. I've seen we've got 2 in the chat, but I'll just ask the first one. And it's probably linked to how you assess the conditions dynamically. This is from Paul. Yeah. Is it about assessing the conditions dynamically to capture the when and how that you mentioned? So when and how we do things.
Yeah, definitely. We should analyze everything from a dynamic point of view. One of the limitations of the first study that I show you is we took a photograph over a period of time, and that photograph, we're assuming it is a representation of all conditions. We need to take time series analysis. We have to do analysis over a period of time. We need to analyze all the factors. And this is what we did more in the second and third project, because of course these were led by professors or people who understand the concepts and much better than when I was doing just a PhD. And they identify, okay, what happened with high wind speeds, low wind speeds. And it's not only the wind speed. If it is wind speed, is high pressure wind speed, low pressure wind, but also what is the temperature of that wind. When the wind was really hot, we have a strong advection in the area. For example, in the western side of Parramatta, then we see that considerably affects the cooling effects of greenery or the spray systems. The next day, you have a completely different story with cool easterly winds flowing from the Parramatta River, and then you have a much pleasant environment. That's why we need sensors. We need constant monitoring. And that's what I'm trying to do in future in my research, have platforms that can show you the dynamic changes of these temperatures over the whole city. So you can see really trends that varies over the time, and you identify patterns, and then if these sensors can retrieve real-time data, you have AI, which is artificial intelligence, to process that information, give you a solution, and that solution goes back into the sensor, and the sensor says, release water. Now is the time to release the spray water, or now is so high the humidity, let's avoid using spray systems, let's turn on the fans because we need air. And these sort of approaches, we use them in some way in intelligent houses or smart houses. We should try to transfer that into the city, right?
What a great way to end a vision for our streets where it's all automated based on real-time data. Fantastic. Carlos, thank you so much for a really, really interesting, I guess, revelation for some of us in terms of the link between climate change and some of these real issues. Really appreciate your time and extend our thanks for you for putting that together for us. So thank you very much. We will make this recording available for everybody. And I think, Sal, how will we distribute that? Will we just email everybody that registered?
Maybe, yeah.
Yeah, I will,
yes,
I will
thank you,
email
Dan.
everybody.
Okay, fantastic. Now, just before we go, thanks again, Carlos. Really appreciate it. Well done.
Welcome. You're welcome.
Carlos.
Thank you very much for the invitation.
Claps for you. Now, just before we go, everyone, I just want to do very quick a plug for the festival this year, the Landscape Architecture Festival, which is called Landescape. Look out for details. It's 12th to 15th of October, interactive session. We're working tirelessly on creating a program for this year, which is based on Reset, and it's a 4-day program for landscape architects. So once again, thanks everyone for joining us. Thank you, Carlos. Thank you, Sally, and we'll see you next time.
Thank you so much. Thank you for the invitation.
Thank you.
And thank you everyone for attending and sticking around up to the end.